Okay, so first we will open Notepad++ as usual, and now we will create a new file, and first we will save this. So file, save as. Okay, so we will writing a source file for the UART receiver. So we will go to the UART project folder and we will select this source folder, right? Now give the file name. So the file name is suppose UART underscore RX for UART receiver. Now select the file type. So file type is basic hardware description language for VHDL. So select it. Now click on save. Now what I will do that I will copy this part of library and entity declaration and I will paste it here so that we can get the framework of library declaration and entity declaration, right? Now remove this generic section from here. We will add generics as per our need for this module little later. Okay. Now coming to the port section. So we will need clock and reset, but we do not need these two inputs here, right? Now, if you remember from our UART receiver module or the block diagram of UART receiver module, then we have few inputs and one outputs, right? So we will declare all the input output ports here in this section. So for this UART receiver module, we will have DIN as an input. So that is input std underscore logic type, and we will be receiving the data at this port. Okay, and we will have one output. So suppose this is dout, that is output type, and std underscore logic underscore vector. So this will be our 8-bit output. if we are receiving 8-bit data on this UART receiver port, right? So this will be 7 down to 0, right? But because we are working on RS-232 protocol and it can support different length of bytes like 5 bits, 6 bit up to 8 bits. So I wanted to make this flexible. Okay. So for this, instead this hard coded 7, I will define a generic and we'll use that generic to define the length of this D out. Okay. So suppose the generic is data width. So data width minus 1 down to 0. So data width will be 8 in this case. So it will become 7 down to 0. Okay. So let's define the generic first here. So we will have this data width that is integer type. Okay. Also, we are needing two additional ports here. One will be input and one will be output. And that will be our interrupt signal or interrupt request, which will be our output type port. And we will have one input, which will clear this interrupt request. Okay. So let's define them as well. So let's give some name. Suppose this is RX underscore IRQ clear, IRQ for interrupt request. So this clear port will be our input type and std underscore logic. And we will have one output. So that will be RX underscore IRQ. So that is our output and std underscore logic. Okay. So what it will do that this RX underscore interrupt request will trigger when all the bits are received. Okay. And we will trigger it for one clock pulse and then we will clear this signal. Okay. And we will clear it by this input signal that is RX underscore IRQ underscore clear. Right. So that's the purpose of these two input output ports. Okay. So we have one more thing to change. So we will change this entity name. Suppose this is UART underscore RX for this module. So I will copy this. So this will be used as an entity as well. And now we will write the architecture for this module. So this will be architecture behave of this entity name is now begin and in the last and architecture or and behave, right? So we have this library declaration. Then we have this entity declaration. Here we have the generic part and we have also this port part, right? And now we are going to use all the modules which we have developed for this UART receiver as per our block diagram, right? So what we are going to use here, number one, that is Baud Clock Generator. Number two, shift register. And number three is Synchronizer. We are also going to write some additional piece of code to interconnect everything in a synchronized manner so that we can get whatever we wanted to get from this module, right? So first we will declare all the components in this module here. Okay, so we are going to use this Baud Clock Generator. So I will copy this part of entity from here and I will paste it in the architecture section, right? Next, we will be going to use shift register. So we have this shift register code here. So I will copy this entity part from here and again I will copy in the architecture component declaration. Okay. Next we are going to use Synchronizer. So I will copy this entity section from here and I will paste it here as well. Right. Now because these are not entity here but these are components, so I will change this entity keyword with the component. Okay. So this is a component here. Okay. So I will copy this and I will replace this and entity name with and component. Same here and component, right? Entity. So this is component and this is component. Okay. So now we have declared all the components here in this module. Okay. So let me give a quick brief what Baud Clock Generator is doing here. Because if you remember that we have designed this Baud Clock Generator for our UART transmitter module, right? And we were using this to transmit the data one by one. And what this Baud Clock Generator was doing, that it was generating the pulse that when each and every bit will be transmitted. So this module was controlling the time, or you can say bit period of that module, right? Now, because you are sending the data at some specific time interval that is defined by your bit period, so at the receiver end, we also need to receive those bits at the same bit period, right? Because these are controlled by some specific time. And on that time period only, we have to receive or we have to capture that input data. Okay. So that is why we are using this Baud Clock Generator module here as well in the receivers module. Now the next module is shift register, right? So what it is doing in the receiver module, so it will convert the serial data that is receiving at the receiving port of this module, and it will convert it into the parallel data, which is the actual data that we're supposed to receive at this module, right? Because we are going to receive data one by one at this receiving port, and we have to retrieve the 8-bit data from this module. Okay, so this thing will be handled by this shift registered component. Okay, and next is synchronizer. And now this synchronizer will synchronize the input signal that is received at the receiving port with our FPGA baud frequency. Okay, and why this is important? Because we can receive the data at any point of time at the receiving port. So that is asynchronous in nature. So we have to synchronize that input signal or that asynchronous input signal with our FPGA baud frequency. And that's what this sync module will be doing. Okay. Okay, so now this is the time for port mapping of these three components. Okay, so I will copy this part from here and I will paste it here. Okay, so now we will write the framework, or we will change the keywords for the port mapping. So that will be written after this begin keyword in the architecture section. So to instantiate the component, we need a identifier name for this component. So give it some name. Suppose this is rx underscore Baud Clock Generator. Now colon. Now we do not need this is keyword here. Now generic map. Okay, so now we will map the generics. So we have data width, we have system clock frequency, and we have baud rate. So this data width will be our data width, right? So if you remember that our data width is 8-bit. So this Baud clock generator will generate 8 pulses here, right? But if you remember about the RS-232 protocol, which we have discussed, so before you started receiving, it will transmit the start bit first, right? So that start bit will be received first at this module, followed by the actual data, right? So what we need, that we need one extra pulse from this data width, right? So this data width will be data width plus 1 here in this case, right? Now comma, and next is system clock frequency. Okay, suppose system clock frequency is 50 megahertz. So this is 50 megahertz, right? And even let's don't hard code it here. Instead, I will prefer to use a generic for this system clock frequency and baud rate as well, so that we can use this code on flexible system clock frequency and flexible baud rate, right? So let's say this system clock frequency is system clock frequency, okay, and this baud rate is mapped to baud rate of this module. Okay, now we will define these two generics in the generic section or generic declaration section. So this is here. So we have this system clock frequency, and that is integer type. And next we have baud rate, and this is again integer type, right? Okay, so now go down. Okay, so we are here, right? Okay, so this is good. We completed the generic map for this Baud clock generator. So next is port map. So before this, let's remove this semicolon here. Now this is port map. Now first two signals are clock and reset. So these are very straightforward. So clock will be connected to clock and reset will be connected to reset, right? Now we have one input and two output here, right? So let's say that this start signal is connected to the start signal, and this baud clock is actually connected to the baud clock of this module. So this will be baud clock, right? And see, this ready signal is also connected with the ready signal of this port. Okay, so now we need to declare these three signals. So let's give some comment here. So let's say declare it. Okay, we will also declare this baud clock. So declare it, and we also need to declare this ready signal. So let's declare it. Okay, we will do it later. Now coming to this shift register module. So let's instantiate this shift register module. So give it some name. Suppose this is rx underscore shift register. Now this is shift register. We do not need this is keyword here. Now generic map. Now this data width will be the data width of this module. So data underscore width. Now we are not doing data width plus 1 here, right? like we did in this Baud Clock Generator. Okay, because we did this here because we are supposed to receive one start bit additionally apart from the data bits, right? But here I am more interested in the data width or the actual data. So I will ignore the start bit here. Okay, so I do not need this additional bit here. So our data width will be our actual data width of this module. Okay, now this MSB or LSB, so we know that we are going to use RS-232 protocol, and that will transfer the LSB or the least significant bit first, right? So I will say this is L here for this UART receiver module, right? Well, we do not need to define this as in generic because we know that we are working on the RS-232 protocol for this UART receiver module, right? So I will just straightforward map this LSB to this generic, right? So that's complete our generic mapping. So let's remove this semicolon from here. Now it's time for port mapping. So port map. So what I will do that I will copy these two statements from here because these are standards and I will paste it. Okay, so this is clock and this is reset. Now we have this shift enable. So what this shift enable is doing here that when we receive this shift enable pulse at this shift register module, then we will capture the input data received at the input port, right? So this is actually the output of our Baud clock generator, right? So what I will do that this shift enable will be connected to the Baud clock signal. Okay, so this will be connected to the Baud clock signal. Now we have this D in and D out. Okay, so this D in must be the synchronized version of our D input. Now, if you remember what we have defined in the entity section for this D in, so which is input type, but this is asynchronous in nature. And for this shift register, we need to synchronize it, right? And for this, we will going to use this synchronizer module, right? So suppose let's give it some name and we will assign that synchronized signal to this D input. Okay. So suppose let's say we have an internal signal that is named as RS synced. So this RX sync will be the synchronized version of our D in signal or D input, right? And our output is very straightforward. So that will be our final output. So this will be connected to D out, right? And that's it. So that's our port mapping for this shift register module. So let's remove this component keyword here. We do not need this. And let's remove this component keyword from this Baud clock generator module as well. Okay. Now let's come to the synchronizer module. So first we will give it some name. So this is suppose rx underscore sync. Okay. Now let's remove this is keyword from the last. Now generic map. Okay. So ideal state. So again, we can define a generic here and then we can map that with this ideal state. But for this RS-232 protocol, we know that our ideal state is logical high, right? So I will map it directly with the logical high. So let's map it. So this is 1. Now let's remove this semicolon from here. Now port map. Okay, so I will copy this clock and reset part from here because these are our standard signals. So these are clock and reset. So clock is connected to clock. Reset is connected to reset. Okay. Now asynchronous. So if you remember from the synchronizer module, then we are receiving this asynchronous signal as an input and we will get the synchronized version of this signal at the output, right? So this async signal is actually our input port of this module and this is D in. So let's copy and let's paste it here at this D in. Okay. And what we will get at the output. So our output will be this rx underscore sync, right? So let's copy this, right? So that's complete our port mapping of synchronizer as well. So let's remove this AND component section here because we do not need this. And okay, so we have to remove this AND component section from here as well and from here as well, right? So let's see what extra signals we need to declare. So we need to declare this rx underscore sync and everything else we had defined here. And everything else we also defined here, right? So everything is good. Now this is the code which is interconnecting all of these components here in this UART receiver module, right? And we have used couple of internal signals as well. For example, this start, this Baud clock, this ready, etc., right? But till now we have not defined that when this start pulse should be given. Means that must be given when we have received the start bit at the reception port of this UART receiver module, right? So for that, we need to detect that start bit for this RS-232 protocol. And how we are going to do this? So we know that for RS-232 protocol, we are supposed to get logical high when it is in idle state, means when there is no data transmission, right? And when there is some data to transfer or when there is some data to receive, then we will supposed to get logical zero as an start bit. Okay. So basically what we need to do that we need to detect that falling edge on this D input, means when we are getting the transition from state high to state low, this means that we are about to receive some data at the reception port, right? So first we will write the code to detect this falling edge on the D input, right? And for that we will design a registered process block. Okay, so let's go down and let's write a process to detect this falling edge on this D in signal or D input, right? So first we will give it some name. So suppose this is falling edge detection. Now this is a process, and because we are designing a register process, so clock and reset will be in the sensitivity list. Now begin. So first we will write the structure for this process block. So if reset is equals to high, then do something, else if at rising edge of clock, then do something, and in the last and if, right? So this is our framework. Okay, so now let's write the logic for this. So how we can detect this falling edge on this D input. So for this, what I will do that I will create a new signal which will be delayed by one clock cycle of our synchronized input. Okay. So let's say that signal is rx underscore sync underscore delete. Okay. And this will get the value of rx underscore sync. So basically what this statement will do that it will transfer the Rx sync data to this Rx sync underscore delayed signal after one clock cycle. Okay. So now we have two signals which is carrying the same data, but the delayed signal is capturing that data after one clock cycle. So we can use that thing to detect our falling edge. How? So for this we will use condition. So what I will say that if this Rx underscore sync is actually 0 and this Rx underscore sync underscore delete, this signal is actually 1, then we will have the falling edge, right? So let's create another signal to detect this falling edge. So let's say this is falling edge detected. Okay. So this will be 1 because we have detected this falling edge, and all the conditions other than this if condition will have falling edge 0. And in the last and if. Now, if you confuse about how we have detected this falling edge with these two conditions, then take a pen and paper and design this, right? So first draw one line and suppose this is 1, okay? And this is Rx underscore sync signal, and at this point it is going to loop, okay? So what we have said that we have another signal that will follow the data of this signal, but after one clock cycle, right? So this is 1. So this is 1 up to here, for example, and after one clock cycle, it will be 0. Okay. So this is our Rx underscore sync signal, and this is our Rx underscore sync underscore delete signal, right? Let's map this together. So at this point, we have to detect this falling edge, right? Because this is our falling edge here, where Rx sync goes from logical high to logical low, right? So at this point, you will see that this Rx sync is 0, but Rx sync delete is high, right? Because for this delayed signal, this transition from 1 to 0 will happen after one clock cycle. Okay, so we will detect this falling edge here. So that's the condition here. So that is Rx underscore sync is 0. So Rx underscore sync is 0, but Rx sync delete is 1. So we will have this falling edge. So we give it some name. So that is falling edge detected. And for any other situation, this falling edge is not detected, right? So that's the whole soul story. So let's remove these two lines, and I will mark this as a comment that we need to declare it later. Okay, so we'll declare it. And in the last, we will have this and process. Okay. So by using this falling edge detection process, we have managed to detect the falling edge on our synchronized input signal. So now we can detect the start bit. But there is a problem. And the problem is that this falling edge will be detected for all the state transition from 1 to 0, right? And that is our start bit, but that can also have our data bit. So it will detect all the falling edges present in the input signal or present in the input data, right? So we cannot use this falling edge detected signal straight to capture the start bit, right? Because every time it detects 1 to 0 transition in the data signal, it will treat it as an start bit, right? So we need to tell our module that only the first transition is actually a start bit. And after that, we will have our data bits. Okay, so before writing that section of code, let's also give the reset condition. So first I will say that do not detect the falling edge in the reset condition. So I will copy this statement here and I will paste into the reset condition. And I will also say that the rx underscore sync underscore delete should have some defined state, right? And I will prefer to choose logical high here because in the ideal state, our RS-232 protocol is about to receive logical high. Okay. So our this Rx sync delete version or this delete signal will also be logical high. Okay. So that's complete our falling edge detection. And now we will write the code for detecting the start bit. And that will be our first falling edge only. Okay. So what I will do that I will use a finite state machine for this purpose. Okay. So let's see how we can design a finite state machine. So for this, first I will create a data type for finite state machine. So let's declare it first. So we will declare it inside the architecture and begin section. Okay, so this is the section we will declare. So write type. Now give it some name. Suppose this is state. So type state is, now suppose we have three different states. So first state is ideal when we are about to receive logical high. The next state will be collecting the receiving data. So give it some name. Suppose this is collecting Rx data. And we will have one more state, that is all the data bits are collected. So let's name this collected, right? So we have three different state. Number one is ideal. Number two is collecting the receiving data. And number three is all the data bits are collected. So collected. Now we will define a signal based on this new data type. So this will be our signal and give it some name. Suppose we are giving this C state for current state. So this will be our current state and that is state type, right? Now go down and now we will write the FSM to detect the first falling edge only. So that will be our start bit. And after this start pulse, we will trigger our Baud clock generator, which will generate pulses to capture the input data one by one. Okay. So that's the whole interconnection. So first what I will do that I will copy this section of code and I will paste it because I need a registered process block for this finite state machine. Now first I will change this name. So now this is our finite state machine. So let's give it some name. Suppose this is RX finite state machines or RX FSM. Now this is if reset condition. So that's okay. And now just remove this section of code from here. Okay, so now we will define the finite state machine. So first we will write the basic structure of finite state machine with the help of case statement. So let's define the case statement. So case current state is, now this is ideal, then it will do something. Now when it is collecting Rx data, then it will do something. Next, when data is collected, then it will do something. And we will have one extra condition, when others. So everything else will be covered in this when others condition that might come because of any bug or hardware failures or environment or other different scenarios, right? And in the last AND case, right? So that's our case statement. Okay, so now we will define that how our finite state machine will drive, right? So what will happen when the state is ideal? So from moving this ideal state to this collecting Rx data state, we have to detect the falling edge, right? So simply code this. So what I will say that if this falling edge detected is equals to 1, then our current state will be our next state. So that will be our collecting Rx underscore data and if, right? Now we are this collecting Rx data. So we need to tell that from which condition we are about to move from this state to this state. So when we will move, when all the data bits are captured by this receiver module and we have collected all the receiving bits, right? So if we are using 8-bit data, then we will capture 9-bit including the start bit, and then we can move to this collected state, right? But if you notice on the Baud Clock Generator module, so here we have this Baud Clock Generator, we had one output and that is ready. And what it was doing, that this ready signal goes high when all the bits are transmitted, right? So here we can use this ready output to detect that if all the bits are received at the receiving end or not, right? Because it was 0 when there is some transmission of data, and it was high when there is no data of transmission, or in ideal state this is high, right? So what I will say, that when we are at this collecting Rx data state, we will monitor the ready signal. So what I will write, so if ready is equals to 1, then we will move to the next state, and the next state will be collected state. Okay, now and if now we will jump to this collected state. So what will happen at this collected state? So first we need to trigger the interrupt signal or the interrupt request signal. So what I will do, that we will trigger this Rx underscore IRQ, that will be triggered. So that is 1. And after this current state will move to the ideal state, right? Now because we have inserted this Rx underscore interrupt request signal, so we have to clear it as well. So what I will do, that I will clear it after 1 clock cycle. So when we are at this ideal state, I will write one additional condition here, and that is if our input, that is Rx underscore IRQ underscore clear, if this signal is triggered, means when this is 1, then we will clear this Rx underscore IRQ request. Okay, so this will be 0 here. And now and if. Okay, so what will happen, that so first we will be at this ideal state, and now when we detect the first falling edge, then we will switch our current state to this collecting Rx data. So we are at this collecting Rx data. Now it will collect all the data receiving at the receiver end. Does not matter if it is logical high or logical 0, right? And once all the data is received, means when this ready signal is high, we will move to the next state, and the next state will be collected. Okay, so what will happen, that this Rx IRQ will be asserted logical high, and our next state will be ideal. So these two things will be happen for 1 clock cycle, because after 1 clock cycle our current state will be changed to Rx ideal, and here we will clear this Rx underscore IRQ request based on this input port. Okay, so this state machine is detecting the start bit. It is not just detecting the falling edge, but it is only detecting the first falling edge or first 1 to 0 transition, right? But if you look at the Baud clock generator, we have still not defined this start signal, right? So let's define that when this start pulse is given and when this start pulse is 0, right? So this start signal means that when we are about to generate pulses at the Baud clock generator to receive or to capture the input data, right? So if we detect the first falling edge, so that is here, and we are just moving from ideal state to this collecting Rx data state, at the same time we have to start, or we have to give this start pulse as logical high, right? So what I will do, that I will say that when this first falling edge is detected at the ideal state, then our start signal will be logical high. Okay, now because this is high and we want it to high for 1 clock cycle, so as soon as we move to the next state, so that is collecting Rx data state, that should be 0, right? So what I will say, that at this state, the very first thing that it will do, that it will trigger this start signal to 0. Okay, so this start signal will only be given for 1 clock cycle only, right? Okay, so let's also give the others condition as well. So when our state machine or the current state is not landed into some defined state, then our current state will be ideal state. Okay, and now we will also give the reset condition. So what will happen at the reset condition? So first our current state will be ideal. Okay, so that is here. Our interrupt request signal is 0. Let's copy this. we don't have any interrupt request at the reset condition, and this start signal will also be 0. Okay, so that's our reset condition. Okay, so that's our VHDL code for this UART receiver module. But there are a couple of more things we need to think of. And let me tell you what are those. Now, if we move to this Baud Clock Generator, so this module will start generating the pulses right after this start signal is triggered, right? And if those Baud clock pulses are about to land at the same time for the transmitter and receiver, then the problem is that we won't be able to get the right data at the right pulse. Because whatever I will transfer from the transmitter module that will receive at the receiving port, and then we will use a synchronizer because that data is asynchronous in nature, and then after 2 clock cycles it will be captured by the UART receiver module, right? So it will be a big synchronization problem. So what we will do as a good practice that I should expect to receive the data at the middle of 2 successive pulses which are coming from the transmitter module, and that will guarantee that we are about to capture the right data at the right bit. So think a bit like this. Let me explain this. Suppose this is clock signal. At this point of time, we are transmitting a bit based on the Baud clock generator, right? And at the same time, we are generating another pulse for this receiver module. So suppose this is receiver and this is transmitter. Okay. So if these two pulses are at the same time, so at this receiver, we will not be able to get the right data for this data bit, right? But if at the transmitter, the first bit is transmitted here and the next bit is transmitted here, and if we capture this data, not here, but at the mid of somewhere here, and this data at the middle of something here, so that's guaranteed that we are about to receive the right bit. So this bit will be received at this point and this bit will be received at this point. So there will be no synchronization problem. We would be getting this data 100% correct at the middle of these two successive pulses, right? So this is our bit period and this is also our bit period, and this bit period and this bit period is always same. So that is 1 bit period, suppose. Okay. So this is 1 bit period, and also this time gap is actually 1 bit period. Okay, so actually the bit period is actually same for both transmitter and receiver, but what we have to focus on this first bit. So what will happen, this first pulse, if we manage to trigger this pulse at the receiver at half of bit period, so suppose this is half of bit period, and then all the pulses after 1 bit period, then our purpose will be solved, right? So we have to write this additional logic for our receiver module, and that can be only happen from the Baud clock generator module because we are using that for generating these Baud clock pulses, right? So what I will do, that I will move to our Baud clock generator. So this is our Baud clock generator module, and here we can see this bit period process where we are defining the bit period of our pulses, right? But the problem is that we have also used this bit period or this Baud clock generator module into our transmitter module, and that logic is also correct. We are needing just additional logic for our receiver module, and that is the bit period for the first pulse must be half of our bit period, right? So we cannot modify this whole program or this whole module for the UART receiver module because that will affect our UART transmitter as well. So what I will do to differentiate between transmitter Baud clock generator and receiver Baud clock generator, well, we can have two options. Number one, you can create a separate module for this Baud clock generator for the receptor or for the receiving module, that is UART_RX. But because these two modules are inside the one big module for the UART transmitter and receiver, so if you write the another Baud clock generator module, so that will generate additional resources on your physical chip. So what I will do, that I will prefer to change our existing logic for this Baud clock generator to make it flexible for the RX receiver module as well, right? So first we need to differentiate it that it is working for a transmitter or for a receiver, right? So for this, I will create another generic that will tell either this module is for receiver or for transmitter. So we can use a simple Boolean generic. Let's give it some name. Suppose the generic name is RX true or false. Okay, so this is Boolean type. Okay. Now I can use this rx underscore true to define that if it is working as a receiver module or for a transmitter module. So let's see if this is true, then this is a receiver. Else means if it is false, then it is for transmitter. Okay. And now I will also create one constant for half a bit period. So we have a constant and that is half of bit period, that is integer type. And let's copy this. So that calculates our 1 bit period, right? So the half bit period will be divided by 2, or this baud rate multiplied by 2. Okay, so the system clock frequency will be divided by twice of baud rate. So we will get this half of bit period. Okay, now coming to this bit period process. Now remember that I have said that all the other pulses except the first pulse will continuously follow the 1 bit period. I mean 1 full bit period, right? And that is 8.7 microseconds for the baud rate of 115200. So we need to only control the first pulse of this Baud clock generator, and that will be half of the bit period. Okay, so these line of codes, so that will be absolutely same, because for all the other pulses other than the first pulse, it will calculate 1 bit period for 1 pulse, right? So for the first pulse, I will modify our code here. So what I will say that if our generic, so what was that? So that is rx underscore true. So if this rx underscore true is equals to true, then do something else. We will have this bit period counter that is 0. Okay, so that is, and if, so if this rx underscore true, then our bit period counter will be half of the bit period. So we have defined the constant for this, or even we can use this bit period here and we will divide it by 2. Okay, so that will also work. So we do not need this, I think, because that will work. Okay. So now I hope this should solve our problem between the receiver Baud clock generator and transmitter Baud clock generator. Now because we have changed its generic, so we need to update our transmitter module and our receiver module as well. So let's quickly update those modules. So this is our UART underscore transmitter. So we must use Baud clock generator here. So this is our Baud clock generator and we are about to use this additional generic here. And we also need to look about the instance for this Baud clock generator. So this will be false here in this case, right? So that is our transmitter module. Now let's update our UART receiver module. So we need to look for the Baud clock generator component. Now let's update this. So rx2 is Boolean. Now let's move to the instantiation. We also need to update this here. Now this is here. Okay. Okay, so that's everything is done. Now this is the time to define or to declare all the signals we have used in this program. Okay, so we have this start. Okay, so let's define a signal. So this is signal start, that is std underscore logic type. Let's copy it. We need to use this statement multiple times for multiple signals. Let's see what else we have. So we have this Baud clock. Okay, so signal Baud clock is declared. We have this ready. So we'll declare this as well. What else we have? We have this rf underscore sync. So that is again std underscore logic. Okay, so that's good. What else we have? We have this falling edge detected. So let's declare it. Okay, anything else? Let's quickly look over it. Okay, so we have this rx underscore sync underscore delete. We also need to use this, and everything else is defined. Okay, so let's replace this, and we do not need this now because everything is declared. I think we are good to go. Okay, let's save this UART underscore transmitter as well, Baud clock generator, and UART receiver. So now we will open Model Sim Simulator, and first we will compile our code to see if it is having any syntax error or not. Okay, so we will open Model Sim Simulator. So this is our Model Sim Simulator. Okay, let's maximize this. Now because we have updated this Baud clock generator module and UART underscore transmitter module, So we need to compile both of these modules once again. But before that, let me quickly add this UART Receiver module into this project. So click on Add to Project and then Existing File. Now click on Browse. Okay, so select the UART project folder. So we have our file inside this src folder. So select this and we have this UART underscore rx. Select this, click on Open and now click on OK. Now we will compile all of our module at once. So I will right click here and then compile all. Okay, so everything is good except this UART underscore receiver. So let's double click on this error. Okay, so let's see what are the error. Okay, so we have declared the rx underscore sync. Okay, so we have defined this as a signal, so we cannot instantiate with the same name. So let's give it some name, component. Okay, component. So let's save this. Now close, recompile. Okay, we still have one error. So what it is saying, okay, yeah, we have a couple of extra lines. Okay, let's save this once again. Now let's compile. Okay, so compile of UART underscore rx.vsd is successful. So our VHDL code is clear from any syntax error. So now this is the time for writing a test bench for this UART receiver module, and then we will test it. Okay,